hydrogen instead of coke. So that will be a carbon dioxide free or carbon footprint free process. So there are many applications that actually people are envisaging, and that I will show some of them: heating, dredging, cooking, health, agriculture, carbon cleaning. So these are all applications that we are looking for now. So I also talked about on-demand hydrogen. So on-demand hydrogen is one of the important factors that we are looking for, because hydrogen carrier is not at all safe. Even storage is not at all safe. You can understand you are actually storing a hydrogen bomb in your home if you store hydrogen. And when there is a on-demand, there is no transportation, so carbon low footprint, low carbon footprint. And as I said, hydrogen is burning at high temperature, so it should be higher efficiency compared to the present system. So there are many ways. One of the two main ways was to obtain hydrogen was actually get hydrogen from natural gas. So think about the methane. The methane CH4. If you actually mix with high temperature steam, then it will oxidize to go to carbon dioxide and hydrogen. Okay. So mostly today's 98% hydrogen is coming from this. This is called grey hydrogen. So 1 kg of hydrogen, to get 1 kg of hydrogen, you are actually liberating 8 kg of hydrogen. So that is the catch basically. And other process is electrolysis, one of the other processes. The electrolysis is very simple process. You take 2 electrodes, okay, you apply voltage or current in between them, you apply voltage, the water will be separated to hydrogen and oxygen. That is the technology that has been launched since long time is existing. But then people have come back to electrolysis technology because it has advantage of scalability, it has advantage to get high efficiency. So 56 to 73% is not bad, but still it is a low energy density because low energy because you want to get hydrogen almost like very high percentage. So we will be able to get around 80, 90% of hydrogen. That's the challenge. So what I conclude from this was electrolysis can be used because we can use green energy, because photovoltaic is there, so we can use green energy to electrolyze water to produce green hydrogen. One of the few bottlenecks are there. It's a low energy efficiency, as I already said, electrolysis, and you absolutely need distilled water, because if you use other kind of water, there are a lot of ions that actually block your electric surface, and your energy efficiency and your actually cell is dying after some time. So basically, that ions you see when there is a glass in your home. You drink water or you take the tap water, you store it, after some time there is a thin, white thin, mostly calcium oxalate, all these phosphates, oxalate, all these things are there. So that actually form a thin film on the electrode surface and decrease the electrochemical performance. And it is very bad for, it's unstable in tap water, so as I said, and hydrogen is very highly flammable and flammable to store, and it is expensive to transport. Okay. So that's why we are talking about on-demand green power hydrogen, because we do not have to transport, and if it is a green power, then carbon dioxide footprint is less. So now here to develop such system, the main important thing, as I said, that electrode. We talk about electrode because we are actually passing the voltage between two electrodes. So electrode is the key because it will give you say HER, you are talking about hydrogen evolution, oxygen evolution. So one side hydrogen, other side oxygen, the two electrodes. So the electrode has to be highly efficient in the sense that it will require lower energy to break, and it has to have a long lasting activity. This whatever electrode you make in the laboratory, it has to have a minimum this long lifetime greater than 10 years. Of course, for manufacturing, for commercial application, it has to be low cost. And so most of the time, what we do is when we when you actually get, there are two different kind of metal working for two different processes. But it will be interesting if it is like a single surface, single material works for both hydrogen evolution and oxygen evolution. So that's called bifunctional catalyst. So if bifunctional catalyst will be interesting for manufacturing electrons, so that your process, your industrial process will be easier. There will be, if you want to synthesize such electrons, it will be cheap. You do not need high temperature, all those things, which is or high pressure, which is required specialized kind of expertise. Anyone can do it, layman can do it, that kind of thing. And it has to be environmental friendly. It has to be low temperature, simple scale. So, as an electrochemist, I started with this program, and then I was exploring this one. So in the meantime, what I was asking, that what was the process that would be interesting to synthesize such electrodes. So one of the process that came to our mind was biomineralization. Biomineralization is something that biology in bacterial bio entity like bacteria, fungus, all these things, they actually millions of years they have made some materials, some artifacts. Okay. So for example, pyrite. Pyrite is one of the ore for iron. Okay. But pyrite is formed with the bacterial sulfur from bacterial biochemical process, and iron ore, whatever iron sulfide are in there, iron ore, so that it forms iron sulfide. So this is the one of the example. So what it does, there are bacteria called sulfide-resistant bacteria. This bacteria you can easily recognize. In Calcutta there are many canals. Okay.
Yeah, so there are a lot of students who have joined right now. So can you just take 2 minutes to brief the background whatever you discussed before in so that they can catch?
Yeah. So thank you sir for the question. So for the students who have just joined, so I am actually trying to show some process or some manufacturing process where we can make a electrolyzer. Electrolyzer means you actually electrolyze water or you pass voltage between two electrodes to get hydrogen. Hydrogen, you already all know that hydrogen is a green fuel, and it is actually helps to world to decarbonize, because some of the fuel that actually produce carbon dioxide, carbon monoxide, like let's say hydrocarbon based, any fuel that you see, diesel, petrol, coke, all these things, coal, all these things produce carbon dioxide to for energy application. But now in the future or today's fuel, we are just talking about hydrogen, because hydrogen is very simple to get. In water, you have 2 molecules of hydrogen, 1 molecule of oxygen. So it can be easily obtained from water. So now today's economy that people are talking about, hydrogen economy, that is yet to come, but that is not very far away. And some of the company like us, we are actually thinking of making such systems very efficiently so that effect of hydrogen comes to your home tomorrow. So to make such such systems, the biggest challenge is to make a sustainable electrodes. Sustainable electrode means we are talking about just passing voltage between two electrodes. So we have to make very highly efficient electrodes so that we get hydrogen at very low energy. That is the challenge. So to come up to that stage, we took a path. It's called biomineralization. I think some of the students already learned about biomineralization. Biomineralization is nothing but the mineral, it occurs through natural chemical process or biochemical process of a bacteria. Okay, bacteria, it provides different kind of biochemicals. Some of the bacteria actually transport currents, so people are using microbial fuel cell. Some of the bacteria gives chemicals, so that chemicals can be utilized for making new type of compounds that can be helpful for or utilized as a catalyst for hydrogen production. So one of the important bacteria in the nature that you get a sulfur reducing bacteria. The activity of sulfur reducing bacteria is very interesting. You have a canals, open canals in your close by your home. It smells, it stinks. So it stinks doesn't mean that it's bad. It stinks that it is a biochemical that is being forming, and that odor is coming to your nose. That is what it is like, you are sensing. But that is a biochemical. That's a chemical process from a biology. So sulfate reducing bacteria, what it does, it actually takes sulfate, like in a lot of food waste, there are a lot of sulfate, sodium sulfate, potassium sulfate. That actually produce HS minus ions, or let's say H2S. It has a smell of rotten eggs. That's why you are getting bad smell. So that H2S actually it is coming from HS minus ions. It is producing H2S, and it actually can produce at the outer layer of the bacteria, or can produce outside. Like bacteria can eject chemical in the environment. So when it is eject chemical in the environment, it produces H2S. The H2S smell is coming to your nose. That is what you are sensing. So that we are actually able to utilize to produce different kind of catalyst. That is what we are actually innovative process that we have patented. So it is important because it is very interesting because it is abundant in art. So bacteria everywhere. So you do not have to go and search for bacteria. Okay. And it is a low temperature process, large scale. Suppose you have a big tank with a lot of bacteria, you can make big electrodes. As simple as that. And it doesn't need very high temperature, it's cheap, environmental friendly because bacteria is doing its own work, you cannot stop it. So you just have to extract energy from it. So here comes our innovative process where we talked about nickel, copper, iron, bismuth, manganese, all these metals. Okay. If there is a bacterial solution is there, you just dip it inside the bacterial solution, then you do not require the temperature. We can actually modulate bacterial concentration, modulate time, or even modulate temperature. Reaction path, basically the size of the reaction path and the volume. So we can get higher surface area catalyst. Okay. The advantage is that it is reproducible. Most of the time in chemical laboratory, people who have done chemistry or metallurgy or material chemistry, getting reproducible data itself is a challenge, especially in the commercial level. Laboratory in 1 centimeter, 10 ml solution, 20 ml solution is easier. But when you want to replicate that in 1 liter or 20 liter or maybe 200 liter, that is a challenge. So here the bacteria advantage is that it's very highly reproducible even in large scale. So now, just wanted to see how the surface of a bare metals, like suppose you put this one inside a bacterial solution, you see the metal surface is completely changing. There's something is happening because the black surface is there, right? So something is happening. That is something that you see here. Okay. So the small cluster of nanoparticles is almost like 100 nanometers. Okay. The interesting part is this bacterial synthesis. Actually, I was collecting water from different kind of canals, from Kolkata, from Bombay, Delhi, then Chennai. All the dirty canals where people do not like to go. I was taking the water from there, and I was actually synthesizing this kind of material, and I was seeing what is exactly on the surface. Whether it's depending on the place that you are able to get in this one. The interesting part is, except nickel and sulfur, there is nothing, no other surfaces is interesting because it's a dirty water. So you expect there will be something on the electric surface. But exactly nothing was there except nickel sulfide. So this was characterized further by iron, electron beam microscopy. We cut the surface, we saw that around 100 nanometer of nickel sulfide surface is on the electro surface. So there is another interesting point that I want to tell. The story is like this: that suppose you make a catalyst layer. So there is a screen printing electrode. It means you just paint it like a painter. Or screen printing is like an industrial process. You just take it with this one. But when we are talking about hydrogen evolution or oxygen evolution, or even the ceramic you talked about, that actually delaminate. Catalyst layer tends to delaminate because you are putting from outside. So here actually you think of, you have a surface which is upper surface is exposed to the bacteria, that upper surface is only converted, but they are actually attached to the surface down. So basically you actually say that this surface won't be delaminated, won't easily be delaminated, because it is actually from the electrode surface. It is attached to the electrode surface. I did not do anything from outside. In chemical synthesis, you can make a nickel sulfide and then put it on the electrode surface, but after sometimes it tends to break. So that is interesting, but these surfaces won't be delaminated from the electrode surface. The stability of the electrode will be higher expected than normal stability, normal other processes. This is kind of electrochemistry, no need to please understand. Only thing I want you to understand is that this is an electrochemistry where it is showing that this material is electrochemically active. Simple, as simple as that. It is active. It is not passive. It may help you to get catalytic property, just it. And it is better compared to other processes, like I tried electrode deposition, the blue one, and hydrothermal processes. When I do hydrothermal or electrode deposition, our current density is much lower. It means we have a low electrochemical surface area, low surface area, current density is low. It means we are not able to get high current from that. Our desired property is high current density. So that is one more important thing. Suppose in case your bacteria, one day your electrode is gone bad, like this. Earlier my electrode was like this, something like this. My electrode is gone bad during experiment. So what I do is I put it again in the bacterial solution and I form exactly similar surface like earlier. So it means, think about a business model. Like people just complain that my electrode is not working, my electrolyzer is not working. So I said, okay, take my electrode, I will regenerate it as a new one, I will replace it and I take back to my industry, I again put it in the bacterial solution, regenerate and give as a customer. So I do not lose anything. Like I have a nice business model. It has shown the stability. It's like 120 hours, during 5 days, continuous 5 days I have shown here. So if it is a straight line, it is more or less stable. What I did is I applied a current. I am measuring the potential with respect to time. Not very difficult to understand. And then compare with different kind of electrodes. Platinum is a known catalytic electrode and bare metal is here. And this one you see here that our bacterial catalyst electrode is around 2.5 straight away. It is not changing. There is a change because there was no solution. So again we added the solution, electrolyte solution, and then there is no change, almost no change. So what I can conclude here, that bacterial catalyst electrode is quite stable even in wastewater. Wastewater is a heterogeneous water. There are many ions, many things. It's not a distilled water. Distilled water, there are no ions. But heterogeneous ions, it is working perfectly fine over 5 days. But whereas platinum electrodes start to degrade after 2 days. Is the potential is increasing, further increasing. Now I want to see what is the efficiency of that system. Okay, I was like